Kampampati, who was initially supposed to be here, but due to Air Canada strikes, he couldn't make it. Nevertheless, I think we're going to hear a very interesting talk remotely today. So, Professor Subbaraman is a professor of computer science at Arizona State University. He studies fundamental problems in planning and decision making, motivated in particular by the challenges of human-aware AI systems. He's a fellow of AAAI, American Association for the Advancement of Science, and ASEAN, and a recent recipient of the AAAI Patrick H. Winston Outstanding Educator Award. He served as the president of AAAI, a trustee of the HCI, the chair of AAAS Section T, and a founding board member of Partnership on AI. Kampampati's research, as well as his views on the progress and societal impacts of AI, have been featured in multiple national and international media outlets. And so if you haven't watched his lectures on AI, they are available on YouTube. And he's an excellent teacher, which is kind of evident from the AAA award that he got. And he has been doing very interesting work in the space of LLM reasoning and planning. So I think today he's going to talk about do LLMs reason? If so, how, right? So thank you for the talk, Surya.
Okay, thank you. I am assuming you can hear me and see my slides.
Yes.
Okay, unfortunately, I can't see you guys, but I will assume that there are throngs of you out there and listening to me intently. Anyway, so I'm going to talk to you about how do LLMs reason. And I should say that when professors give talks, it's typically essentially a sort of an umbrella or a compilation of what their students are doing. And you can see my students on the bottom left-hand side. It's a somewhat a tad smaller group than the one that Sharath seems to be running. But we have some interesting work that I wanted to talk to you about. Before going forward, as was mentioned by Sharath, essentially, I did want to come directly in person to MILA and your group and talk to you guys, if for nothing else, but for the fact that this would have been my Rihanna going to Ambani's movement, for those of you who keep track of Ambani's in India. And in saying so, I'm not necessarily saying I am Rihanna. I'm saying your group certainly is the Ambani's, seems like the Ambani's of the French Canadian AI. Okay. There seems to be somebody who has a microphone on, but they might want to stop it off. So before I go forward into the talk itself, I just want to mention that somewhat in contrast to many LLM talks, this is a little less of a rah LLM, my God, how great they are, etc. It's not because I don't think LLMs are amazing technology. They're quite amazing technology. But I tend to think that there is also a significant amount of misunderstandings, both from the researcher side and, of course, from the public side. And I kind of say that the problem with alchemy is not that chemistry is useless, but that people wanted to delude themselves that chemistry, a pretty amazing discipline, can become nuclear physics if only you prompt it in a certain way. So it's like understanding what makes them work, what doesn't, what are their capabilities, what aren't their capabilities is much more interesting to me. And so this talk might sound more skeptical than many of the LLM talks that you might tend to hear. And again, as I say, I think of skepticism as a soft inductive bias for good science. It's not meant to be like unending negativity or crazy hype. It's just understanding what technology is, what are the limitations of a technology, helps you improve it. Okay, so as Sharath pointed out, I basically worked in planning much before all this stuff on LLMs and reasoning came along. So I come to reasoning from the planning side. Planning is a form of reasoning. It is a sequential decision making and reasoning about actions and change. So I sort of looked at LLMs and their capabilities from that perspective. And I don't need to tell you, given the titles of all the talks that you guys have been giving over the last 2 days, I don't need to tell you what is the current state of art in LLMs, but just to be on the same page, we have the standard LLMs, the GPT-4. When I say standard LLM, I say something up to GPT-4, but without basically the quote unquote what has been called the reasoning models. And then they are essentially there's that side, and then there's the reasoning models which started from O1, R1, and of course a whole slew of them right now, which basically had to add two things to standard LLMs: test time scaling, which actually makes quite a bit of sense in terms of why does it work. They're using LLMs as generators and using verifiers of some sort in the loop. And then the other point is post-training, which is instead of doing it in test time, you can do it in training time with respect to synthetic data and try to compile this into the generating LLM and hope for a better performance of the LLM without any additional test time scaling. So that's basically the state of the art, and at least in the way I look at it. And then the thing that you're hopefully going to get out of this talk, and I'm trying to just give you a summary before we go into the actual talk itself, is so the messages I'll try to send you is LLMs trained just on web corpora have been known to have severe limitations on planning reasoning tasks. We've done a bunch of work showing this. And there's like several papers, including in URIPS 2023. There are like 3 papers there, which basically the standard LLMs, up to GPT-4, basically don't do well in planning tasks. And if you thought they were, then I'll try to explain to you why the distinction, why people tend to think that they're doing planning. Essentially, as I'll show you, they do planning when planning is actually not needed, where the goals are basically completely independent. But on the other hand, LLMs are actually great arbiters of style. And so they are like a generative AI system. They learn style. Style is a global distribution level property, and correctness is an instance level property, and LLMs are much better at style, which is pretty impressive because we never had anything that captures style as well. So in fact, we ourselves have used LLMs as behavior critiques to kind of, critique undesirable robot behaviors, where the behavior is undesirable in terms of some implicit constraints that people might have in their mind. But LLMs can still be used as generators in a generate test cycle to provide robust planning performance. And there are multiple ways of doing this. The simplest ways have been things like self-consistency, where LLMs will generate multiple choices and then you try to take the majority choice. Or a better version is you can have a verifier in the loop, which basically either takes the correct choice or at least gives criticism on the incorrect choices, so that LLM basically has a new candidate generated conditioned on the criticism. And that's what's been LLM-Modulo. I'll talk about that. And then these improved reasoning abilities in this generate test, that basically you can think of it as a kind of a test time scaling, can be compiled back into the base generated LLM with either SFT or RL. RL has become like the buzzword right now, but I will show you, hopefully, that the way DeepSeek RL works, and as we know, really, to be completely honest, we only know one example of how RL is working in any frontier model, because most of the people have stopped actually publishing. And so DeepSeek RL certainly is actually very close to just being a sort of an incremental filtered SFT. And so it can be compiled back into the LLM so that hopefully its performance might improve. The resulting LLMs that we have started calling LRMs, and it's sort of caught on, and some people actually call them LRMs, large reasoning models, still have no correctness guarantees, but are actually better generators. And so in some sense, post-training incrementally compiles the verifier signal into the LLM. It's a theme that I'll keep getting back to as we go forward. And then finally, in trying to understand the reasoning models, there's a huge amount of mythos that developed in terms of what to make of the intermediate tokens. Essentially, the standard LLMs, given a prompt, will just give you the solution as the completion. Now we are training LLMs to, given a prompt, give a bunch of intermediate tokens followed by the solution. In fact, you can completely demarcate the intermediate tokens. Unfortunately, they get demarcated in things like think, stop think, and then solution begin, stop solution. And so these think, thought, think are the intermediate tokens have essentially started being given lots and lots of undeserved properties, such as that they'll tell the end user as to how LLM is actually reasoning in solving their problem. And so if you're not sure of the solution, you can look at the reasoning trace and figure out whether the reasoning is correct. And I'll push back pretty hard on that because I think that's actually, unfortunately wrong. So anyway, that's basically what I'm going to talk about in the talk today, and obviously it's a whole lot to cover. So there is actually a 3-lecture series that that was recorded like about a month back in Italy in summer school. That if you are interested in specific things, you can go back to look at that. Actually, we did add additional new results in this talk towards the end, but if you want more of the background, you can go back to that. Okay, so getting onto the summary and getting onto the talk. So as I said, standard LLMs can't plan according to our studies. And the idea basically, and what we do, we actually use the usual planning benchmarks that have been used in the planning community, which are actions being sequentially done to achieve goals. And then we found essentially over a period of time in multiple papers that essentially they do pretty badly in even simple things like blocks world. And while the performance seemed to improve from one standard LLM to another, there's always a question as to whether in fact this is the improvement is because of the memorization or because actually they learned how to do planning. And then that's why we talked about something called mystery planning domain that I'll talk about in a minute. So again, in general, to me at that time, it wasn't surprising that standard LLMs basically are sort of more like a external system 1 rather than system 2. And so I didn't expect them to have much of a planning abilities. Furthermore, generative AI in general and LLMs in particular essentially capture the distribution of their training data. And style is a distributional property. So they'll give you something that looks like a plan, but correctness of the plan is an instance level property. And so style and correctness are not actually perfectly correlated, even though historically and even in terms of our human civilization, we tended to assume that good style meant good content, but that's not actually fully correlated. And in fact, you can show that in the case of LLMs by systematic empirical studies. Okay, so that's worthwhile keeping in mind. One other thing, in terms of the perspective on LLMs is you cannot ignore the memory effect of LLMs. They are essentially sort of doing some sort of approximate retrieval on the huge amount of training data they've been trained on. And we just don't have very good sense of what that training data is because we're doing web scale or world scale training. And so some interesting correlations of this, corollaries of this is, for example, people tend to assume that LLMs actually take more time versus less time in guessing the solutions for a problem, depending on how computationally hard or easy it is. This has come back actually in the reasoning models in terms of the length of the reasoning traces. If the length of the quote unquote intermediate tokens is longer, it must mean that the problem is harder. I'll show you that that's actually not at all true. You can set up clean experiments to show that much simpler problems, basically might take much longer. As an example, we'll see that a transformer trained on really complex mazes does much worse on a scenario where in fact there are no obstacles at all. So you have a no maze. So you have start here, goal here, you just have to go directly. Any search algorithm will take much less time. The transformer trained on mazes basically dies because it doesn't know how to solve this simpler problem. And the reality is that the effort is not connected to the complexity of the problem, it is connected to the training data, which is hard to characterize because we are talking about training data, spanning the world. one corollary of this is that people tended to, for example, assume that generation, if plan generation is hard, maybe plan verification is easy. But it turns out that's actually just a wrong, corollary. That's a wrong intuition. In fact, we have a paper that I'll talk about in iClear this year, which was actually done earlier, showing that LLMs are actually no better at verifying than they are at generating. On the other hand, of course, as you all know, LLMs are great for background knowledge. This is very easy for them, and much has been made of traditional AI's ability to deal with getting the right knowledge, relevant knowledge to come to bear on the problem. But then, because LLMs have been trained on the web scale collective knowledge, they're pretty good at common sense, domain knowledge, theory of mind, analogies, not perfectly good, but they'll do a sort of a mediocre, okay job on lots and lots of things. And that is actually nothing to sneeze at, because we never had any AI system capable of doing that. Okay, and of course, I didn't even get into the summarization, etc. aspects, which are very, very impressive for LLMs. Okay, so I did mention that, if you look at the results here more carefully, you'd see that as the models improved, their performance in certain kinds of planning problems, the ones, for example, blocks world is a very simple domain, this seemed to improve. But then there is a second row called mystery blocks world, where they seem to be basically doing pretty badly. These are the standard LLMs. And what we did essentially in terms of mystery blocks world is, to actually understand memory effect, you need to do diagonalization. You need to come up with problems that are probably not going to be in the training data. So one idea was that we had essentially was take something like a standard blocks world domain and change the words. So for example, instead of picking up a block, we'll call it attacking an object. Instead of saying unstacking a block from top of another block, we'll say feasting object from another object. And it turns out that the words are different. In fact, you can also have a random strings instead of any English tokens. So these are called the mystery domains, where essentially you are just sort of obfuscating the domain. From a classical planning perspective, from any kind of a reasoner perspective, both the problems are equally easy and they're equally actually isomorphic, but LLMs just die on the second one because they are essentially because their memory effect doesn't help them in the second one. So that's about the mystery domain. Now, of course, there's a number of things, ideas, interesting ideas that came up, chain of thought, React, fine tuning, etc. It turns out they don't actually help much. I don't want to go into too much details because that's an entire separate talks that are available on the web. But we have a paper on chain of thoughtlessness and analysis of COT in planning at NeurIPS, by the way. So just imagine getting a paper with the title chain of thoughtlessness into NeurIPS, given that you guys, the grad students, are the ones reviewing it. So that's sort of high water mark for interesting titles that we got through. And then there is a paper that sort of shows that chain of thought reasoning doesn't scale. Essentially what it does, for example, as you can see on the right hand side, especially look at the last letter concatenation, which is a very, very simple kind of reasoning problem compared to even planning problems. All you're doing is, given k words, you want to get the last letter of all the words and put them into a sequence. You all know this. And in fact, original chain of thought paper by Jason V and co. essentially made this big deal that if you actually just give an example and tell it how to do the last letter concatenation, it can take that advice and then just go to town with it. But they checked it only for the size of problems that they originally checked without the advice. But if I tell you how to do last letter concatenation and show an example with 2 or 3 words, you should be able to do it with 10 words, 20 words, 10,000 words. You may be bored to death, but you have no problem in actually doing it for longer words. And this basically results show that as the number of words increase, that is, the length generalization doesn't really happen. Basically, whatever boost that you got with the chain of thought advice just fades away as the number of words increase. That's one of the main points of chain of thoughtlessness. And then React is a kind of a cousin of this idea. And then we have a paper in TMLR basically showing React has some of the same issues, maybe even more baroque. And that you might be interested in looking at. So again, these ideas are good, but they don't necessarily do the change in terms of actually reasoning, the reasoning performance. Once again, things like mystery domain, they're actually very bad, but even for normal things like last letter concatenation, they seem to be doing very badly. You should be surprised at this. If you're old enough, I know that most of you in that room are probably not old. There's this guy called John McCarthy who essentially said that the whole point of AI is to come up with an a program that takes advice from humans, because advice taking is actually quite hard. Advice taking and applying it generally is, AI complete problem. So that last data concatenation example made me think of this joke that, there's this capitalist proverb that, give a man fish, you feed him for a day, teach a man how to fish, you will feed him for life. But really, with LLMs, you have to give fish, you will feed it for a day. If you tell it how to fish 2 fish, you can feed it for 2 days. If you tell it how to fish 3 fish, you'll feed it for 3 days, etc. In the sense that it just doesn't take the advice and apply it as the length generalizes. Okay, that's the one to keep in mind. Now, despite what I said, obviously there are like tons of papers, more of the papers with more citations, cumulatively for sure, than the ones we wrote, saying that LLMs indeed actually do planning, and that they're actually doing quite well, etc. And so there's bunches of them. There's some examples here. And so the question is, what exactly is the disconnect here? The disconnect here is worthwhile understanding, because planning, as used in common parlance, involves like two kinds of things. One is knowing what actions are relevant, what are the preconditions, what are their effects, what are the general types of plans, the types of old plans that worked, etc. That's basically planning knowledge. The other is the generation and verification techniques, which is making sure that the actions don't go into each other's way. Essentially, they will provide, if you achieve a goal and then you do an action that undoes the goal, then you don't have the goal by the end of the problem. So interaction analysis winds up being very important. And plan generation and verification is the second part. And interestingly, LLMs are actually amazingly good at the first part. That is the planning knowledge. If you know of this thing called MacGyver series, some of you may have seen MacGyver. They're like MacGyvers. They will come up with all sorts of potentially reasonable actions for solving this problem, but then they can't guarantee that there are no interactions between them. On the other hand, traditional planning techniques, traditional AI reasoning techniques, start with actions that are like a small number of actions that are well modeled, and they focus a lot more on the search and the interaction resolution part. Full planning requires both of them. LLMs only do the first one well, the second one they're not actually doing well. So that's the way to understand why people thought LLMs are doing planning, because they're actually using them more for action selection rather than to actually make sure that your goals don't have interactions and your plan actually works as advertised. To show this, we took Block's World and essentially removed all the interactions from them. Block's World, by the way, for those of you who may not have heard about it, is just a simple, the kids' Block's World, where you kind of put named blocks which are in one configuration in the initial state into a different configuration in the final state. So if A and B and C are on table, you may want to put A on top of B on top of C and C on top of table in the second, final state. And then you have things like stack and stack, put up, pick up, put down kinds of actions. So interestingly, what we show essentially is if you take the Block's World, the way sub-goals interact in any world is, for example, there can be, first of all, actions can get into each other's ways, and in the planning parlance, actions not only can make certain conditions true, they can make certain conditions not true. Those are called the delete lists. So if you remove delete lists, and if you also remove preconditions, that means actions can always be done and they will give their intended effect, even if in fact the feasible requirements to be able to do that action are not present. If you remove them, Block's World then becomes a world full of sub-goals such that you can work on each of the sub-goal and just concatenate them in any which order and the plan will work. And what we showed basically in that New RIPS 23 paper is that if you do this kind of relaxation, essentially LLMs start doing better performance. Notice that the green part increases as the level of relaxation increases. This is sort of important. So you might be wondering, why is there still some red? Because partly LLMs have to count the goals that they have to satisfy and make sure that all of them are satisfied. And sometimes the bookkeeping fails there. And so these are all with GPT-4 results. And so they actually, that's the part of thing that fails in terms of LLMs based planning. So I tend to, in respect to that, I kind of say that, there was this old thing that became pretty popular. Recent thing is pretty popular by this woman saying that I want AI to do my laundry and dishes so that I can do art and writing instead of the other way around. So in the case of planning, I would say actually any LLM can give you a great plan to travel to Montreal or a great plan to do your wedding. Okay, getting a wedding plan is not hard. But the reason whether or not a wedding actually goes right or whether or not a plan to come to Montreal actually executes right depends on all sorts of logistics interactions. And so my suggestion is if any of you are ready to get married and you're looking for ideas, ask ChatGPT only for higher level ideas, and you still have to figure out, make sure that all the logistics work out correct. And so what really should be the goal of AI is that you want to focus on the big picture and the AI should focus on the small picture. But in the case of LLMs and planning, it wants to focus on the big picture and it'll still leave you all the small pieces that should be in the right place at the right time so that the marriage will go on. If this is making you wonder what is going on with the whole agentic revolution, the reality is that, and if you actually look at the benchmarks for agentic LLM evaluation, most of them more or less assume there are no interactions between actions. In fact, just the other day, I was asking somebody, what sort of interactions do you have in this particular agentic benchmark, which is a pretty well-known one, I forgot the name, and it turns out they don't have any interactions at all. And so they basically are assuming that the LLM is being used to figure out what tools to call, and any reasonable order of calling them will lead you to the correct outcome. This should not be surprising because LLMs actually don't have planning capabilities. And if they don't have planning capabilities, if you start executing in the world, if the world is non-ergodic, that means you can actually get into bad states and not be able to come out of it, then that is actually a safety issue. And the safety with respect to agentic systems is probably one of the bigger things that should keep people awake rather than AGI killing us all. Okay, so that's about actually just a short, I was hoping it's a short thing about standard LLMs. But then I want to go into what's going on in the reasoning systems, the reasoning model. So how would you go from a standard LLM, which is sort of a system one, wannabe, to something which actually can do more deliberate tasks? One simple idea is essentially to do generate test. So the idea is let the LLM generate candidate plans and figure out among these candidates which are best, or then loop until the candidate plan becomes better. There's a bunch of ideas that have been tried. The whole self-consistency sort of ideas are one, but the one that I actually like a lot more, and it's become quite popular afterwards, more recently, is this whole issue of having a verifier in the loop, and then the LLM essentially becomes a generator of candidates, and you have a bank of critiques, a bank of verifiers, some of which may actually be LLM based, many of which may actually be coming from outside, some of which may be code based verifiers where the code itself is separately generated by another recursive call to LLM. So this is sort of what we have called LLM-Modulo framework. There's a bunch of literature on that, including there's a paper in ICML 24. So there you're just really using it as a generate test framework where LLMs are actually generating the next candidate, and the critiques are saying what's wrong with it. Either all of them agree, or if they don't, they will provide, this is the reason your candidate plan is incorrect. So you're just basically giving this as a back prompt, and whether or not the next candidate actually takes this back prompt completely into account is not guaranteed, but the next candidate hopefully will be different, and then the critics again will check if the candidate passes all the tests. If so, you send it out. So if you look at this, for example, program synthesis, most of the techniques that are actually being used for program synthesis right now with LLMs, which have any kind of a guarantees, include this. Essentially, the LLM generates code, and then you have a bunch of unit tests. You provide the Python code to a Python interpreter along with the unit test, see what the code does, and compare it to what you are supposed to get for that particular unit test. And then if it is wrong, then you basically ask, okay, you're failing on this, and then you wait until this loop converges. In the case of cursor kind of things, the human becomes the verifier instead of these actual machine verifiers. But I'm not more interested in machine verifiers right now. So this is sort of important to understand that we are actually talking about critiques rather than solvers. These critiques essentially look at different pieces of the plan and say whether or not they're happy. So for example, in a temporal planning scenario, one might look at causal connections, one might look at resource usage, one might look at temporal constraints. And if all of them are happy, then that's sort of like all the unit tests are passing, and then you send the plan out. And we showed that, in fact, with even standard LLMs, with this kind of test time scaling, with this kind of LLM-Modulo technique, you can improve performance quite a bit, not just in the benchmarks that we looked at, such as international planning competition benchmarks, but also things like the OSU has this travel planning domain, and Google had what I call their own Google natural planning domain. We looked at all of them, and essentially in all of these cases, you can actually improve performance by this sort of generate test view. Okay, one important thing I want you to remember is we're looking at critiques and verifiers rather than solvers. There is a much more simplistic idea, which is just use LLM to go from natural language to some formal description of the problem and give the formal description to a classical solver. That is underselling LLMs in my view. In fact, LLMs are much better than that. And in fact, and one of the other problems with that is if the classical solvers tend to be non-compositional, if you have a solver for doing, let's say, things which doesn't have temporal constraints and you want to add temporal constraints, you have to redo the whole search again. Whereas critiques can be compositional, and that's a very useful thing. And I talk about all of this in the ICML paper. You might be interested in looking at it. And then you can also actually provide guarantees, just like unit test passing kind of gives you at least the guarantee that none of the known problems are present in the code that you're sending out. If the critics are happy, then modulo the critics, you can essentially make sure that you can say that the plan is correct. And the completeness comes in terms of whether the critics are able to look at whether the LLM is able to generate all kinds of plans, all kinds of potential plan candidates, and that's where things about prompt diversification and meta controller comes in. You might look at the ICML paper. I kind of make a connection between what goes on in the meta controller and things like a tree of thoughts idea. Okay, and then the types of critiques in LLM can be a variety of critiques. They can be correctness critiques, which is very important. You can also have style critiques. LLMs are much better for style. Correctness, they tend to be classical critiques, but style, basically, you tend to have, it's a much more amorphous thing, and so LLMs are actually much better for that. Critiques can be just binary, like try again, or constructive, so pointing out errors. And by the way, in terms of the critiques, you can also have synthesized code, LLMs to synthesize code for the critiques, which will then be used in a second LLM-Modulo loop. And that's actually something that one of my students, Atharva, actually did in his MS thesis more recently. And so that's sort of the different types of LLM critiques. And as you're listening to this, one thing that even if you've never heard of this stuff, you probably know the whole about RLVR, RL with verification in the loop, verifier in the loop. What are these verifiers? Verifiers are critiques, and they're coming out from somewhere. And typically, for most of these problems, the critiques are coming out from outside of the LLM itself. So there is the tendency to say that maybe LLMs can critique themselves, correctness. So LLM generates a plan and checks if it's correct or not by generating another prompt to saying, is this plan correct? And then goes into this loop. That makes no sense from the perspective of complexity. From the perspective of complexity, verification is cheaper than generation. But then both of them are reasoning problems, and LLMs are not necessarily good in trying to solve the problem in any standard way. So we show in the iClear paper that there are cases at least where if the LLM tries to second guess itself to check whether or not its solution is correct, its performance worsens, mostly because it can have false negatives. So it might actually have generated by luck, by fluke, a correct solution and then walks right over it and stops with the wrong solution. This is something that is very much possible in the case of LLMs. And in general, LLMs are no better at verification, tabula rasa, than they are at generation. But they're good at style criticism. So this is a paper from COMB last year, where we actually use LLMs to see whether a bunch of behaviors, all of which satisfy the goal, they achieve the goal, but some are more preferable to the humans than others. And these preferences tend to be very implicit. People don't quite write down all the rules. So, for example, in the left-hand side bottom, yeah, you ask the robot to give you a pair of scissors, and it's nicely giving you a pair of scissors, except with the pointy end towards you. And with all the AGI angst, the last thing you want is like a hulking big robot giving a very pointy thing with the pointy thing pointing towards you. That's not a good behavior, but there is nothing wrong in terms of actually giving the pair of scissors itself. So it's correctness, but it's not correct style. And those kinds of things can actually be done, criticized better with LLMs themselves. There are no better techniques than actual LLMs for that sort of stuff. We also used it for human preference proxies, just like that one was the human preferences on the behaviors. Here also you can have human preferences in terms of an LLM can have a human proxy. LLM can act as a human proxy so that the machine can basically, the AI system can see whether or not the solution that it's giving would be kind of palatable to the humans in the loop without asking them. And so actually we did some work that was in HRI last year that shows that there is some hope there, essentially, that in fact LLMs can be pretty reasonable human proxies. And as I already mentioned, I tend to think of LLM-Modulo as a kind of a catch-all way of providing correctness guarantees with LLMs in the loop. So for example, if you think of alpha geometry, alpha proof, fun search, alpha evolve, all of them can be viewed as essentially LLMs as being used as idea generators with external sound solvers and verifiers in the loop. And those are the ones that guarantee that what you give out is actually correct. And as I already mentioned, program synthesis community uses unit tests, which is essentially, again, a partial verification of the code that you're generating. Okay, so that's about test time scaling. The thing that everybody is much more excited about in general is this whole quote unquote, can we take the test time scaling into the training phase? Because one thing that you have to understand is way before many of you in that room probably were born, systems used to be such, the AI system used to be such that you give a prompt and you go home and come back after 2 or 3 days and it would have actually solved the problem because the search is being done online. And now we don't want to wait for anything. We want essentially the solutions as fast as possible. And the computational complexity is conserved. So if you're giving solutions as fast as possible in front of the user, you must have spent the time during the training. There's no way computational complexity will disappear. And so the way in general, Marvin Minsky used to say that intelligence is integrating test part of generate test into the generate part, so that the generator actually generates candidates that are more likely to pass the muster with the tester. And that is a great way to think of what has been happening in post-training with LLMs. So generating, in fact, the way I would enter that is, since we have talked so much about LLM-Modulo, imagine if the LLM-Modulo system was used to solve a whole bunch of problems until the solutions are correct. Then each of the problems that were solved correctly will become synthetic data. This is the problem specifications, is the correct answer. And you can do good old fine tuning that already becomes a form of post-training. I realize that we have an extra kink. We are no longer just doing prompt and the solution. You're doing prompt, intermediate tokens, and the solution. I'll talk to that in a minute. So the post-training techniques essentially rely quite significantly on synthetic data. We have already used all the web that's available. So we solve many problems. LLM solves many problems itself, even though user is not in the loop. And the verifier in the loop, just like in the LLM-Modulo, keeps telling it, try again until this becomes correct. And when the solution becomes correct, it essentially is stored to and trained, used to train the weights of the LLM. And the post-training approaches that, for example, DeepSeek RL uses can be understood quite completely in that perspective, because in essence, LLM generates a whole bunch of trajectories ending in different solution candidates. And essentially RLVR is giving more reward to the things, the trajectories that are ending in verifiable solutions, and sort of push back on the ones which are not ending in the correct solutions, and hope that this way of changing weights overall improves the LLM's generation over quite a long period of time. So LLMs are now fine-tuned not only on the solution, but also on these intermediate tokens. And hopefully I'll have time to talk about this whole mythos of what these intermediate tokens are. It's quite clear that intermediate tokens are helping LLMs. What is not clear is, first of all, two things. One is how are they helping? And second is, should we believe that the intermediate tokens also mean something to the end user of these LLMs? And that second part is completely wrong in my view, and I'll give you some information on that. So RL post-training really can be seen as sort of an incremental compilation of the verifier signal. So you tend to essentially start with a base model that has a reasonable top 15 correctness in the case of DeepSeek, because that's the only one that we know all the details about, DeepSeek R1. 15 top 15 correctness, and then essentially let it generate 15 trajectories for a distribution of problems that are more or less similar to the ones that it can handle, and then hope that at least one of the 15 is actually correct. If in which case, with RL over a long period of time, you can actually make this top K high correctness into top 1 high accuracy. So top K high accuracy becomes top 1 high accuracy on this distribution. And then now you have a better LLM which has higher top 15 accuracy on slightly larger problems, and you can repeat this loop. And that's how you can essentially generate large, solve longer and longer planning problems, or longer and longer last letter concatenation problems, if that's what you're interested in. So that's basically this train, test, and distilled time inference compilation can really be thought of as compiling the verifier signal into the base LLM. And that's basically what we are saying, that during the training time is what basically the DeepSeek was doing. Test time, I would just call it LLM-Modulo. I would say training time is internal LLM-Modulo. When nobody is looking, you're trying to solve more problems with verifier in the loop, and then using that to fine-tune yourself. And then there is this whole idea of distilled time too. You can distill the model that you have can be used to generate trajectories for another model, and that's and then you can do rejection sampling with supervised fine tuning to actually improve like a smaller model, something that DeepSeek R1 talked about, for example. So you can think of this in terms of this inference compilation. A bigger point here in general is machine learning always had this problem of what to do with auto distribution, right? This is just the big problem, right? And it's not surprising because, in fact, all the pack theory, etc., is with respect to in distribution. The question is how to do about pack auto distribution. As this joke on right hand says, if my model can't generalize auto distribution, let's just train it until there is nothing left out of distribution. In some sense, that's what we could say tongue-in-cheek, we have done with LLMs, but that idea works for factual queries because there's only so much factual stuff in the world, and hopefully we wrote it all of it, and then you can train everything, all of that data with LLMs. But the reasoning, especially given this length generalization aspect, there is not enough data. It's not enough to just say how to solve last letter concatenation as a procedure. You have to give large number of last letter concatenation instances of different lengths, and there are infinite number of those instances. And so this incremental compilation winds up becoming the way we are doing. In practice, if you never care about more than, let's say, 100-word last letter concatenation, then you're fine. You can't tell the difference between the fact that it's only good at doing up to 100 words versus something that actually understands last letter concatenation as an algorithmic concept. So in general, this incremental compilation still essentially doesn't give you the full deductive closure, and that should not be surprising. In fact, the top things that I'll get back to in a minute to show that things like O1 reasoning models will improve performance on mystery domain, but as the length increases, they too fall out, in terms of performance. Okay, and this should not be. We are not the only one saying this. For example, this guy who talks about multiplication accuracy, and as the models improve, the multiplication accuracy is improving, but it's never completely correct. And there are other people showing essentially that the multiplication, you have to kind of incrementally compile the ability to do multiplication for bigger and bigger numbers. Okay. One last thing before I get into the O1 results is what are intermediate tokens doing? It's sort of clear, this abstract picture is trying to tell you that if you consider the probability that given a task prompt, LLM gives a completion and that completion has the correct solution to the task, If you consider that probability, that is P1. And if you consider a different setup where the same task prompt is given to the LLM, but with a prompt augmentation, that is after task prompt, you gave a bunch of extra tokens, you can call them intermediate tokens. With this augmented prompt, along with the task prompt, LLM completes, and the question is whether the completion has the solution. The second probability cannot be less than the first probability, if you look at all possible prompt augmentations. And in general, I would argue that much of what is happening in the intermediate tokens is finding, essentially training the LLM in such a way that with the prompt augmentation, it has the ability to fit itself better to the training data, and so basically predict over the instances that's been trained on, predict the completions more correctly. This basically is a view to keep in mind because that would be useful in the later parts in a minute. One important thing in this view of intermediate tokens is that there is no restrictions on the prompt augmentation. They don't have to be English words at all. And all of you know, and I don't have to tell you because you guys are all doing research in this area, that a token in LLM is really a point in the embedding space. Some points in the embedding space correspond to actual language words. Other points correspond to language concepts that don't yet have a word attached to them. And as far as LLM is concerned, the prompt augmentation will work if you actually just take a bunch of points from the right set of points from the embedding space and put them after the task prompt. The only thing really is the intermediate tokens don't have to make sense to anybody. The completion should make sense to the end user. So they should again be essentially points that actually have words connected to them. And this is a useful thing. And some of you might have heard of this in terms of continuous latent space prompt augmentations. So this is actually a way to think in terms of think about intermediate tokens that will be useful. So now coming back to O1, back in like last year when I gave this talk at ACL 2024, a version of this that was at that time O1 is still not out there. Then Noam Brown, when O1 came, basically said, well, Rao said LLMs can't solve unsolvable problems, etc. Look, I was able to have O1 solve it. And so we actually took that as a challenge and did, careful systematic analysis on the reasoning models. There was one in, right there in September 2024, and then a better version of that is actually appeared in transactions and machine learning research. And basically the answer there essentially is that indeed the reasoning models are improving, but as I explained to you, they improve, but the improvement sort of fades off as the length increases. So if you increase the plan length, you notice that the improvement is quite significant for the smaller plans, but as the length of plan increases, the accuracy falls down pretty drastically. There's a whole bunch of other issues that the paper talks about, but this I just want to bring up because it kind of connects to the incremental compilation. DeepSeek R1 is competitive in the same way with O1. We also checked the DeepSeek R1. And if you're keeping up with the news, basically the same thing that we did on O1 back in September has been kind of done independently by a group in Apple. And since it's a group in Apple, of course, all hell broke loose. And then basically there's a lot more interest in saying, oh my God, in fact, LLM reasoning models, LRMs can't actually solve these problems. But essentially they're showing the same exact thing. That is, if you increase the length, the performance falls down, and the improvements is only corresponding to the incremental compilation for the length that you have trained it on. So we did actually get the historical record corrected. New York Times essentially makes clear that we did do this earlier for what it's worth. One other interesting thing is that even with the reasoning, LLM is a better generator. There are no guarantees that the generated candidate is correct. It's just probabilistically more correct. And if that is the case, then I know LLM-Modulo, I can do LRM-Modulo. That means I put the LRM in the the modulo loop. So LRM generates the plans, and then they're still checked by the critiques. And as of now, as we go to press, this is still the only way to actually ensure safety rather than hoping that maybe they will be safe. And in fact, so this is sort of doing both post-training and test time scaling, because post-training has already been done in the LRM, and the test time scaling is being done in the LLM-Modulo loop. And we actually show in that TMLR paper that even performance of O1 can actually be improved further that accuracy improves now, but with guarantees, because not only the accuracy improves now, you actually guarantee it, because a wrong solution would not be allowed to go out by the critics. So that is sort of a way of combining test time scaling and post training. That leads me to actually one of the more interesting parts of the talk, which is like bleeding edge right now. All the other stuff has already been published. This stuff is not, but I'll spend the next 10 minutes as quickly as possible to get you some of the bleeding edge stuff that we are doing. So some of the open questions and misconceptions about LLMs include, first of all, as I kind of mentioned, what's the role of intermediate tokens in LLMs? Are they really supposed to help end users to understand what the LLM is thinking? That has become a somewhat of sad but popular view in some subset of the community, and I try to push back on that. And in fact, and then the separate question is, are interpretable intermediate tokens? So we actually, as I said, the intermediate tokens don't even have to have a form that the user may have to understand if you believe in the prompt augmentation view. So the question is, will you get better performance if in fact they're interpretable? In fact, we'll show that the interpretability and the performance improvement actually are oftentimes at odds. Interpretability to the end user and performance improvement. And the other question is the length of intermediate tokens a reliable indicator of the difficulty of the reasoning problem? Unfortunately, no. Again, I'll talk about some of our results. And then, if I have time, I'll also talk about, is the RL formulation used in DeepSeek LLM post-training really different from incremental SFT? Part of the problem, it turns out that the RL formulation that DeepSeek published actually is a degenerate MDP. It has, it misses a whole bunch of useful properties of MDPs, and because of which actually doing RL there is not that different from doing incremental SFT. And it's shown both by, theoretically as well as empirically in a paper that we have. Furthermore, we actually also show that the length of intermediate tokens increasing has been misread by DeepSeek R1 as RL is learning. And we kind of basically said that we can show, and other people have shown that too, that much of that increase comes because problems which are wrong, the intermediate token length tends to be longer. Problems where the answer is wrong, the intermediate token length tends to be longer. And whether the problem answer is right or wrong doesn't depend on how inherently hard the problem is. I already mentioned this, that intermediate tokens, I want to think in terms of prompt augmentation. And, I don't have to tell you that there's a whole bunch of anthropomorphization of intermediate tokens that's going on. The aha moments, the thoughts, the reasoning behaviors, models are thinking to the problem, they're backtracking, they're self-verifying, and all sorts of such claims are being made. The question is, I want to check whether they're actually believable, because if they're not believable, and you might say, how does it matter if it's just a metaphor? Well, it's not a good metaphor because it engenders false, undeserved trust in the end users. Imagine you ask an LRM an answer to a problem that you can't self-verify because you don't know the answer, right? Because most of the time, AI systems will be used to solve problems for which we don't know the answers. And you're trying to check whether the answer is correct by looking at these intermediate tokens. And if the intermediate tokens are not actually connected to the accuracy in any causal way, then that kind of might engender undeserved trust in the end users. And furthermore, as I'll point out, and I kind of sort of hinted earlier, actually requiring linguistic tokens itself is an albatross on the RL phase. You can actually do better if you don't care about if you think of intermediate tokens as only making sense to the LLM for the user. And not surprisingly, if some of you looked at the open source models that OpenAI released, they actually have 3 parts to the trace. One is the think part, one is the commentary part, and one is the solution part. And as you know, they only show actually, if you are using the commercial model, it only shows the commentary and the solution. They are supposed to make sense to the user. The stuff in the think part, they never show. And they didn't basically left it to your imagination as to what that is. And DeepSeek R1 actually does show it. And then there's all sorts of this mythology that started. We actually, I've been thinking about this for a while, that in fact there's actually a February Washington Post article that describes this. But we have actual technical work pointing out the issues with this sort of anthropomorphization. Specifically, I want you to think of distinguishing between 2 notions of intermediate token interpretability. One notion is interpreting how intermediate tokens seem to help the task performance of LLMs. That's it. Not really about end user. This is a lot more like mechanistic interpretability studies and trying to figure out, let's say, why is this helping? And those studies may well be essentially in terms of activation layers, activation strengths in different layers, etc., etc. That's a mechanistic interpretability study. The other is how intermediate tokens help end users interpret the inner thinking process of LLMs, which is this aha moment, the verification cycles, etc. And I hope to show you some results to show that the first one is fine, but the second one is really questionable. And so coming back to whether in fact they're generating intermediate tokens, basically people just assume that if it's in English, then it must be, kind of reasoning traces. So if you look at actually DeepSeek R1, the real technical advance in DeepSeek R1 is DeepSeek R0, which just uses RL post training and generates, actually has higher accuracy than R1. And they went from R0 to R1 because they didn't like the fact that R0 was combining pseudo English with pseudo Chinese. And they felt that people in America maybe want to have only pseudo English. And so they kind of SFT'd it to hell to actually make sure that everything would be in pseudo English. And then they actually took a performance hit. The paper points out that the accuracy actually went down. There goes your point that, putting restrictions on what the think tokens are doesn't make sense because what you're optimizing is for the accuracy. But then let's look at what DeepSeek R1 does for a simple block solved problem. R1 gives these mumblings. Looks like this is English, right? You can start reading pieces of the English. It looks like English. But if this is a single page, that's one thing. Second page, third page, fourth page, fifth page, 5 pages of pseudo English. I dare you to see people who are actually reading 5 pages of pseudo English for a small planning problem to really understand what's going on in the reasoning traces. Much of this has been dealt with by various somewhat questionable qualitative studies saying basically let's take this whole big thing and let's give it to GPT-4 and make it to segment into various kinds of pieces and see if the relevance, if there are more types of pieces that seem to be problem setup versus verification, is that connected to the accuracy? But it has nothing to do with the end user, making sense of these. So in general, end user making sense of the intermediate tokens reminds me quite a bit about this Rorschach test, where I show you an ink blot test and you will start seeing interesting forms in it, and you will swear that there is a monstrous butterfly on the top one. But I didn't make it monstrous. I just threw in some ink and then basically folded the paper. Because of the way the symmetry occurs and everything, you will start seeing patterns. And that doesn't necessarily mean that that was kind of pattern connected to what was done originally. So then we can start thinking of LRMs really might actually be large mumbling models in terms of the meaning in the intermediate tokens. And so we wrote this paper, Beyond Semantics, that's available on the archive, where we actually, one of the reasons people have trouble in checking whether the intermediate tokens have semantics for the end user is because how are you going to look at 5 pages of English to check whether it actually leads to the solution? It's very hard. It's like very qualitative effect. Instead, what we did was we looked at a star search algorithm solving a bunch of mazes, and then the A star search does intermediate operations such as putting things on open list, putting things on closed list. You take those as the intermediate tokens, and then you basically SFT an empty transformer. And so that's what we did. And so we considered different kinds of distributions of the mazes, Wilson, classical, randomized, etc., so that we can also do out of distribution studies. I'm almost getting there. So the reasoning traces look like this. They're supposed to only kind of make sense to A star search, not necessarily making sense to you, because A star search can recreate these reasoning traces to see if it actually leads to the solution. We can check when after you train the transformer, you can check in the inference stage whether it is actually producing traces that are correct by A star search standards. We basically give these confusion matrices that show that there is no perfect correlation. And in fact, you can have situations where the solution is correct, but the trace actually doesn't lead to that solution. And where the solution is incorrect, but the trace is correct, but the solution, so trace is incorrect. So trace is correct, but the solution is incorrect. So basically, both of them are disconnected, which makes us think, does correctness of the traces matter at all for the training? So do we really want the correct traces only to be provided to the learning stage? Basically, if you think of the intermediate tokens as essentially the ways in which LLM can sort of overfit to the data, then the actual tokens, the correctness of the tokens shouldn't even matter. So what we did was we did the experiment by swapping the traces. So we'll take the problem one, we'll give the intermediate traces for the problem two for the problem one, and the correct solution of the problem one as the solution. And this is the swapped model. And then if the reasoning trace correctness mattered in training, you would expect training test time performance to take a big hit. Turns out, not only doesn't it take a hit, it's actually more effective. It's actually the swap trace model seems to be a little more robust compared to out of distribution. You can look at that in the paper. We also did this for question answer sort of scenarios, and the results are the same. This paper is actually under review right now for one of the ACL conferences. So the results there are the same. And one interesting thing that we did with this question answer one is if you actually care about the interpretability of the reasoning trace to the end user, then you can actually look at the performance versus interpretability. And we compare traces such as the DeepSeek R1 traces, which don't have any interpretability for the end user, presumably, versus traces that can actually, for this particular set of questions, they can be separately evaluated to see whether they make sense with respect to the answer. And the interesting thing is, and so we did human subject evaluation in terms of the end user interpretability, and of course the normal benchmark evaluation in terms of the final accuracy. And the surprising thing is that the most interpretable intermediate tokens actually lead to less performance, and the less interpretable intermediate token lead to higher performance, which again, throws some cold water on that. One last thing here is, does the length of intermediate tokens have correlation with the problem complexity? I mentioned this earlier. So instead of, we train my empty transformer on the Wilson mazes, but we test it on basically no maze mazes. That means there's really no obstacles at all. It's still syntactically the same form as the original maze. And A-star search can solve both of these. And when it solves the second one, it takes much fewer steps. But if you give it to LLM, essentially LRM, it takes the transformer trained, Wilson transformer trained on the mazes, it takes much longer time. So for example, this one shows that the Wilson mazes normally require 1500 tokens for the A-star search correct trace. But for the A-star search, it only takes 30 tokens for the free space versions. And yet the accuracy is much worse for the free space versions for the same model that's trained on the correct, on the more complex mazes, which again tells you that the intermediate tokens are not connected to the problem complexity. They're connected to the distributional difference between what the training data is and what the test data is. And it's a useful thing to keep in mind. There's a lot more studies there that I wouldn't have time to go in. The last thing I want to mention, and I'll stop, is the RL issue, which again, there's a paper, RL name only, which basically looks into the MDP model that was used for RL post-training and points out a whole bunch of degeneracies in that model, including the fact that with that model, basically, essentially, there is very little difference between RL tuning and iterative SFT. And in fact, but the point is, people keep doing these studies and keep saying things are improving. And there's a joke that somebody said that the head spinning RL LLM results. This joke is mine, but somebody pointed out this, that math data on Venn model seems to improve pretty much any kind of RL post-training of DeepSeek style. In particular, with degenerate MDP, RL is close to ISFT, that is filtered incremental SFT, where you let the base model generate intermediate tokens, you use the verifier to reject the ones that are not working, and then you do SFT on the remaining ones. And that becomes very much similar to RL performance. And RL should be a lot more interesting than that, and so it's worth realizing that. And the claims about intermediate token length being reasoning effort become suspect when you separate the reasoning effort into correct versus incorrect responses and find that most of the reasoning token length is higher only in the incorrect responses, not in the correct responses. And the problem complexity has nothing to do with correctness and incorrectness, as we already looked at earlier. And all of this sort of made me think that anthropomorphizing intermediate tokens with reasoning for thinking traces is a bad idea. And so we wrote a position paper which sort of summarizes all of this, and you might want to look at that. So in summary, I kind of told you that standard LLMs have issues with planning, and that there is a clean way to make them generate tests and then improve their performance in the test time scaling. You can compile the test time scaling into base LLM, and that will sort of give you LRM. Post-training incrementally compiles the verified signal, but then the anthropomorphization of intermediate tokens is something that you want to avoid. I told you there's a bunch of other longer things that you're interested in. These are the two short papers that you might look at if you're just looking for like a short summary of whatever I said. And there's a couple of machine learning talks, street talk stuff that you might be interested in too. And I'll just stop there. Thank you very much for your time.
Questions? Thank you very much for this discussion. It's great to see the nuance that you bring on the reasoning capabilities, quote unquote. So my question is actually on this capability. Since you've worked a lot with these model DeepSeek, R1 and O1, do you think that this capability comes from the pre-training, or do you think it is elicited from the post-training? My question is,
I think so. The current post-training. So it turns out that the current post-training, which is basically DeepSeek RL, DeepSeek R1's RL, that's the only one that everybody repeats, basically surfaces what is already present in the base model. So you need to have a base model which is good, which has a good accuracy at top 15 level before this either SFT or RL pushes it towards more correct solutions in fewer shots. So top 15 high accuracy becomes top 1 high accuracy. There are very different ways of doing RL that nobody has. One of the things you just have to remember currently is you don't know how Gemini is doing RL. You don't know how OpenAI is doing RL. DeepSeek guys were nice. They wrote the paper, so we get to either copy them or to criticize them. Science, goes by criticizing and copying it. Whereas if you say we're doing something, we won't tell you what it is. You have no idea what they're doing, and I wouldn't be surprised at all if, in fact, Gemini is doing a very different kind of RL. I actually have tweets about this. When first O1 came, I guessed a particular kind of RL approach for O1 that is closer to essentially AlphaGo and Mu0. And I couldn't be sure what the O1 guys were actually doing. We still don't know what O1 is doing, or O1, O3, and GPT-5 is doing, but we know what DeepSeek RL is doing, and it's not doing that. And if you do that kind of more, powerful RL techniques, then the question becomes a different question. Is it just doing surfacing or not? Currently, we are really just surfacing if you're using DeepSeek RL approach. RL is much bigger than what DeepSeek RL did, okay? But that's really has become the bedrock of all the studies about, this sort of questions right now.
Thank you. So if you were to speculate, would you say that O1 is doing a different type of RL than DeepSeek?
I have no idea. I hate the fact that basically they say, guess what we're doing, but I have no idea. I basically would certainly believe that Gemini is more likely to be doing a very different thing. And I've heard 18th hand, the rumors, the same. One of the things that you guys have to understand, and I've tweeted about this, that Silicon Valley is the best closed open source system that is out there, because people in the labs keep constantly shifting. And so everybody in one lab knows what the other lab people are actually doing. It's the people outside who don't know, who actually depend on the TMLR papers and the NeurIPS papers, and they have no idea. So actually, I've heard like 15th hand that Gemini, for example, doesn't do DeepSeek RL style post-training in the sense that it doesn't just have the base model generate K trajectories and hope that one of them is correct, because that sort of a thing that can actually be very inefficient, right? Because of the 15 trajectories you generated, if none of them is correct, the RL is not getting any signal. Instead, you can spend even more time and do something like LLM-Modulo. And given a DeepMind's background, I would say some sort of an MCT style technique with a verifier in the loop until the solution becomes correct, and then use it for training. And that can be a very different kind of approach, than what you can do with the DeepSeek RL, DeepSeek R1 RL.
Thank you for your presentation. In your conclusion, I guess you mentioned that there is almost no correlation between the size of these intermediate tokens or reasoning traces and the complexity of the problem or the ability of the model to reason, right?
All I'm saying is I was providing you, counterexamples showing that the difficulty of the problem doesn't seem, in this particular case, in the free space case, difficulty of the problem clearly has no connection to the length of the intermediate tokens. The cheapest problems, as given by A-star search complexity, actually are generating the longest intermediate tokens as well as very bad accuracy, while in fact that they're actually easier. So that's my interest is question the orthodoxy, because not too many people are doing that. Okay, because there's a lot of interest in the in the companies themselves to just say the good part about the models. And so if there is something I can tell, because many of your grad students, consider being skeptical. Okay, and then see, because it's easier actually to get papers when you sort of agree with what everybody is saying, but you should consider, are there counterexamples? And this is definitely one counterexample.
Yes, but I think we can see this reasoning traces as just computation scaling. And in your example, like this maze, I think it's just a synthetic, simple toy example. But in more real world problem, we can see people are recreating the gold medal in IMO with
again,
just by scaling and self-criticizing the model. And I mean,
so
how we can explain it?
My point is, first of all, two issues, and I'll just push back on this. And because my Twitter is fully about pushing back on these kinds of questions, they're very relevant questions, and just want to point out that saying real world doesn't mean a damn thing, because IMO stuff has been done with humongous amount of post training on IMO style problems. You know that, I know that. So if you actually have ever set exams, I can't tell whether you're a student or a faculty member. If you're a faculty member, you will realize that the hardest part is setting exam questions that are interesting and that are not easily accessible to people who have just memorized the solutions. And every possible crazy style of IMO problem has essentially been, lots of them have been put in the training data. And so I wouldn't necessarily assume it's great that we can do IMO, but it's also, you have to consider the fact that you actually use significant amount of resources in, many of these problems, many of these approaches, based on informal accounts, generate like thousands or millions, thousands or tens of thousands of extra synthetic problems that they will solve with a lean verifier in the loop, and then actually post-train themselves. And so it's the fact that what they're doing essentially is they're taking more of the out of distribution in distribution, which is still consistent. So that's why my argument is, if you really want to understand out of distribution, you have to do diagonalization arguments. You have to set up the problem rather than just assume it's working well. Remember that planning was already working well, quote unquote, with standard LLMs. So in fact, one of the funny things is, for the first 2 years, first 1.5 years when we were doing this work, everybody will say standard LLMs are already doing planning. But if they really meant it, they wouldn't have needed reasoning models, right? I mean, why do you need reasoning models if the standard models are already doing reasoning? We knew they weren't. They were essentially showing memory effects in certain cases. The robustness has significantly improved with this incremental compilation.
Okay, any other questions? If there are any questions online, like, you can unmute yourself and ask your question as well.
By the way, one thing I really feel sorry about is the reason although I did in tongue-in-cheek Rihanna and Ambani's, The real reason I wanted to come is to talk to the students. And, obviously, Charlotte seems to have a very big group of very bright students. I would have loved to spend the rest of the afternoon basically letting you yell at me and push back. But, you can still do that either now or by email to me or, post on Twitter, and I'll get back to you.
I think you can still visit us after, like, whenever you have time. So
yeah, by that time we'll have a different talk. So I want to answer the question on this one.
Okay, well, if there are no more questions, let's thank Professor Rao once again for this great talk.